Hello, children. Welcome back to another session of States of Matter. So, we are continuing with the states of matter. In the previous sessions, we have completed gas laws, Boyle's law, Charles' law, Avogadro's law, Gay-Lussac's law, ideal gas equation. All gas laws we have completed, and still few more gas laws are there. Under that, the most important one is Dalton's law of partial pressures. Dalton's law of partial pressures. What is meant by this Dalton's law of partial pressures? First of all, this law is applicable. It is applicable to non-reacting gaseous mixtures. Non-reacting gaseous mixture. So if you take two or more non-reacting gaseous mixtures, for that particular gaseous mixtures only Dalton's law is applicable. Dalton's law is not applicable to reacting gaseous mixtures. Like let us say if you take NH3 and HCl, ammonia and hydrochloric acid, both are going to react to form ammonium chloride. In such cases it won't react. Sorry, it won't applicable. Dalton's law is not applicable. Okay. So let us talk about statement. At constant temperature must be constant. When two are more non-reacting gases are taken in a container of volume V. So volume is also constant, vessel volume or container volume of V. Two or more non-reacting gases are taken in a container of volume V if you take it, and the total pressure exerted by the system is equal to sum of partial pressures exerted by individual gas molecules. Statement wise it may looks little lengthy, but it's a very simple statement. Let us say you have taken two gases in a container. The total pressure exerted by the container or the system is equal to sum of the pressures exerted by the two gases. I mean to say P total is equal to P1 plus P2 plus P3 and so on till it is applicable to till n number of gas molecules. This is the mathematical form can be given for Dalton's law of partial pressures. So now try to verify this Dalton's law statement. Let us verify with two gases. Let us consider volume of container. Volume of container is V, and two gas molecules I have taken. Which are labeled as A, B, and let us say number of moles of the gas A is Na, and number of moles of the gas B is Nb. Number of moles, that is Na and Nb. Okay. We have taken NA and NB. Fine. Now what we are going to do? Partial pressure. Partial pressure. Partial pressure is nothing but pressure exerted by individual gas molecule. Every gas molecule pressure can be taken it as a partial pressure by individual gas molecule. Individual gas molecule pressure is taken it as a partial pressure. Let us say for this gas A, partial pressure is A. For this gas B, partial pressure is B. Let us assume. Okay. PA and PB. In that case, according to ideal gas equation, here ACC, I am writing it as according. Let's just try to adjust according to ideal gas equation. So PV is equal to nRT. But here P is nothing but pressure exerted by the total system, that is P total into V. N will be the sum of number of moles of both A and B. I am considering only two gases, right? So RT. So let us consider it as equation number 1. Now let us say for gas A I have taken, for suppose I have taken gas A. Gas A, what we are going to get it? PA into V is equal to Na into RT. It is equation number 2. Similarly, for gas B. For gas B, what we are going to get it? PB into V is equal to NB into RT. This is equation number 3. Now what we are going to do? This equation 2 and equation 3, both you are going to add. Equation 2 plus equation 3. What is equation 2? That is PA V plus PBV is equal to Na plus Nb RT. Because RT we are going to take it as common, Na plus Nb. And then PA plus PB of volume V is equal to Na plus Nb and RT. Now we check it. Compare it with equation 1. What is equation 1 we have? This is P total, if you notice it. P total, which is in turn equal to which term? PA plus PB. Isn't it? So let us say, consider it as equation 4. Compare equation 4 with equation 1. If you compare it with equation 1, what you are able to get it? P total is equal to PA plus PB. But we have taken only two gases. Like that, okay, many gases can be taken. That means I can write it as, if many gases are there, P total is equal to P1 plus P2 plus P3 and so on. It goes on. Such a way, we will be able to understand that is P total pressure exerted by the system is equal to sum of the partial pressures exerted by individual gas molecules. That we can verify it clearly, right? And now what we are going to do, let us say equation 4 we got it, and equation 2 we have equation 2 also and equation 1 also there, right? What is supposed to do? Equation 2 upon equation 1 you do it. Equation 2 is this one, right? So PA into V, right, which is in turn equal to PA into V, which is in turn equal to, just hold on, yeah, PA into V, if you take it, what we have? Na into RT upon, this one will be P total into V upon Na plus Nb into RT. RT gets cancelled, V gets cancelled. This Na upon Na plus Nb, that is Pa upon P total is equal to chi A, where this chi A is nothing but what? Mole fraction of A. Children, it is an application of Dalton's law, of course. That means partial pressure of A is equal to P total into chi A, mole fraction of A. Similarly, in the same way, Pb is equal to, what you can take it, P total into chi B, mole fraction of the B. This is the relation between partial pressures and mole fractions. So partial pressure of gas A is equal to P total into chi A. Pb is equal to P total into chi B can be taken. Hope that is clear for you, right? So then, as I already mentioned, it is applicable only to non-reacting gaseous mixtures. As I mentioned, it is applicable to non-reacting gaseous mixtures. Like examples. These examples are very important for competitive examinations. H2 plus He and N2 plus H2. Many of the people, they used to ask a doubt, nitrogen and hydrogen, sir, both they are reacting in Haber's process going to form ammonia. Then now we have given it for gaseous mixture, non-reacting gaseous mixtures. Under normal conditions, nitrogen and hydrogen cannot react. We have to apply high pressure and high temperature, right? So that's the reason N2 plus H2 I have taken an example. N2 plus O2 is also one of the example. You can take CO plus N2. That is also an example. H2 plus CO2 and CO plus CO2. That is also an example. For all of these gaseous mixtures, Dalton's law is applicable. Not applicable to reacting gaseous mixtures. For reacting gaseous mixtures, it is not applicable. Example for that, as I already mentioned, NH3 plus HCl. This is one example. SO2 plus O2. SO2 plus Cl2. Right? You are going to get SO2Cl2 in this case, sulfuryl chloride. In this case, you are going to get sulfur trioxide. In this case, you are going to get NH4Cl, ammonium chloride. So such a way, it is not applicable to the reacting gaseous mixtures. Okay. And majorly, this Dalton's law, another important application is there. Another application of Dalton's law. What is that? Many of the gases which are insoluble in water can be collected over water. So gases which are insoluble in water, are collected over water. What I mean to say that, let us say you have taken a container like this. Now it's filled it up with water like this. It's filled up with water. Now through another apparatus or another experiment, you have prepared a synthesized a gas which has been released into the water like this, which has been released into the water. The red color which is indicating the gas, and we are going to collect that gas over the water. In that case, the gas whichever we are going to collect it over water, that gas is to be taken it as pressure of the moist gas. Because it is collected over water, so pressure of moist gas is nothing but pressure of dry gas plus pressure of water vapor. Because this part is occupied by the water vapor along with gas. So that pressure exerted by the water vapor is called as aqueous tension. Now, if I would like to calculate the pressure of the dry gas, then I will apply formula pressure of moist gas minus aqueous tension. If you subtract pressure exerted by the water vapor, you will get the pressure exerted by the water vapor from moist gas. If you subtract, you will get the pressure of the dry gas. Such a way, you will be able to calculate the dry gas pressure. Of course, this formula, again, we will use it in quantitative analysis of organic chemistry by using, for estimation of nitrogen, by using Dumas method. In that case, also pressure of dry gas formula can be used. It is also another application of the Dalton's law. Hope you understand. It is a clear-cut idea about Dalton's law of partial pressures. Hope you like the video. So if you like it, please click on the like button and please subscribe to the channel. And we will, catch up. We will catch up in the next video. Until then, take care. Bye.